This lesson is supposed to teach you to differentiate hard functions that contain exponentials. So by the end of this lesson, you should be able to differentiate functions like 2 to the power of x minus x squared all to the power of 17, or other functions like e to the power of x squared plus 4 all square rooted, or even 1/2 of e to the power of the square root of 3 minus x squared. Once you've mastered differentiating different functions like these ones, I'll teach you one of the weird applications of exponential functions. I'm going to teach you how to figure out how quickly different liquids are cooling down. But without using up any more time, let's talk about further exponential derivatives. Now, this lesson is called More Exponential Derivatives because it follows on from our lesson where I introduced the derivatives of exponentials. So if you haven't seen that lesson, I suggest you watch it first and then come back here, and then you should be able to follow most of what I say. In that lesson, I showed you how to differentiate exponential functions. So we found that the derivative of e to the x was always itself. As we know, e is a special number, and it's approximately equal to 2.71. But if we had another base other than e, then we have to remember to multiply by the log base e of that number. Now remember, the log base e is exactly the same thing as ln, so rather than writing the log base e everywhere, instead I'm going to write ln of a. So the derivative of a to the power of x is the same thing as ln of a times a to the power of x. So the last point I want to make before we get on with our examples is that we can use these two rules over here with all the standard rules of calculus, like the chain rule, the product rule, and the quotient rule, to solve a whole bunch of different problems. Now, I'm not going to be able to give you examples of all of these, but by showing you a few, I hope you'll be able to figure out the rest for yourself. Now, throughout this lesson, I'm going to assume that along with these derivatives, you also know how to differentiate polynomials, things like x squared or x cubed or things like that. So in this case, I want you to differentiate f of x equals 2 to the power of x times the square root of x. I do recommend actually pausing me and trying to solve this yourself, and then you can unpause and watch how I do it. So to differentiate this function, I first want you to realize that we're multiplying 2 to the power of x by the square root of x. And because we're multiplying one function by another function, we are going to need to use the product rule. So to quickly remind you how to use the product rule, you've got this first function, which I've drawn with a circle, and the second function, which I've drawn with a square. You're going to want to differentiate them one at a time. So in the first turn, you differentiate the circle and leave the square, then you leave the circle and differentiate the square. So for starters, I'm going to copy over the functions that we haven't differentiated. I'm going to copy the square root of x here, and then I'm going to copy 2 to the power of x over here. Now, in order to differentiate 2 to the power of x, we need to use this rule over here. The derivative of 2 to the power of x is going to be the ln of 2 times 2 all to the power of x. So now we just want to differentiate the square root of x. Now, I don't usually recommend that people learn any derivatives off by heart, but the square root of x is probably the most important one to know off by heart, because it shows up so much. The square root of x differentiates to 1 divided by 2 times the square root of x. Now at this point, we are technically done. The derivative of 2 to the power of x times the square root of x is 2x ln 2 times the square root of x plus 2 to the power of x times 1 on 2 root x. But I think it might be a good idea to just quickly simplify this just a little bit. The first thing I want you to recall is that you can always rationalize square roots. Like if you had 1 over the square root of 3, you can always rewrite that as the square root of 3 over 3, because you can multiply by root 3 on root 3, and then these two will just give you the 3, and this gives you the root 3 at the top. So therefore, this 1 over root x could be rewritten as the square root of x divided by x. There is one further simplification we can make as well. I want you to notice that in both of these terms, we have a 2 to the power of x and a square root of x, just like we do over here. So I'm going to take 2 to the power of x times the square root of x out as a common factor. At this stage, we've reached our final answer. We can see that the derivative of 2 to the power of x times the square root of x is 2 to the power of x times the square root of x, all times the ln of 2 plus 1 on 2x. Now, this problem showcased how we would actually use the product rule. So now I'm going to give you another problem that's going to use the chain rule instead. So this time we want to differentiate g of x, which is equal to the square root of e to the power of x squared plus 4. Now this may be one of the first times you see this, but this time we do have a polynomial in the power. This is a very useful thing to be able to do, and you're going to see lots of applications for polynomials inside of powers. So for this function, we actually have a function inside of another function, which is also inside of another function. Now, if you remember correctly, to differentiate something like this, we just have to unpack each layer one at a time, differentiating each function in terms of the previous layer. So we're going to start this by first covering up the innermost function, and then we're going to differentiate the square root in terms of this function. As we know, the derivative of a square root is 1 on 2 divided by the square root. But as we said, we're differentiating in terms of the inner function, so we just need to copy the inner function over here. And then we just continue unpacking step by step. So now that we've finished the derivative of the first part, we have to make our way into the next part. So if we're going to differentiate e to the power of x in terms of the inner function, we know that e to the power of x differentiates to itself. So we're just going to get e to the power of whatever we had inside the circle. Now this is one of the funny things about the exponential function. It differentiates to itself. And that's a little bit confusing sometimes because you can forget whether or not you've actually differentiated. But remember, because it does differentiate to itself, we just leave it exactly the same. So now we've differentiated the outer two layers, we just need to make our way into the final layer. Now if we want to differentiate x squared plus 4, that's pretty easy. We just bring the power down to get 2x, and the constant goes away. So at this point, we've actually finished the derivative. The derivative of the square root of e to the power of x squared plus 4 is equal to 1 over 2 times the square root of e to the power of x squared plus 4, all times e to the power of x squared plus 4, all times 2x. But again, just like the last example, you really shouldn't leave the derivative like this. It's barely usable in that state. So what we're going to do is we're going to simplify it again. So I've copied it down here. Now the first thing we can do is we can cross this 2 with this 2. Now the next thing we can do is we can replace this square root for the power of half. And since it's reciprocal, we can also replace it for the power of minus half. Also, we can just place a power of 1 over here. Now to finish this off, I want you to notice that this is the same as this. So we can just go ahead and combine these two with index laws. Notice that 1 minus 1/2 is the same thing as 1/2. Now I'll take this x and put it out the front, and I'll replace this power of half for the square root, because it looks a little bit nicer. So our final answer is that g dash x is the same thing as x times the square root of e to the power of x squared plus 4. Now it's crazy how much you can simplify something like this if you just try. And most of the time when there are exponentials involved, because exponentials differentiate to themselves, you usually can simplify things quite a lot. But at this stage, I think we've just about completed this example. So at this stage, I'm going to give you one more example that's a little bit more applied than the last two I gave you. So in this problem, we're investigating the temperature of something like a cup of tea. This model over here is a pretty good model for the temperature of a cup of tea once it starts cooling down. We're basically saying that in a 25 degrees Celsius room, the temperature as a function of time can be given by 25 plus 75 e to the power of negative kt. So the idea here is that for this cup of tea, we start off at 100 degrees Celsius, and the cup of tea is slowly going to cool down until it ends up at a temperature of 25 degrees Celsius. If you give me a particular time, I'm going to be able to tell you what the exact temperature is at that time. So the two questions I want to ask here are, if the temperature of the cup is 80 degrees Celsius after 1.2 minutes of cooling, can we find the value of k that actually gives us the correct graph? After this, we want to ask, how quickly is the temperature dropping at that exact time? It turns out that if you change these two numbers here, you're going to be able to change the starting temperature and the ending temperature. Notice that 25 plus 75 gives you this 100 degrees here, and 25 over here gives you the final temperature. So the idea here is that as long as you know the temperature at one time, then you're able to find the temperature at all other times. And this actually works really well. You can try this yourself if you'd like to. So to find the value of K, we know that the temperature, which is capital T, is equal to 80 degrees Celsius when little t is equal to 1.2. So as we said, if you're going to put 1.2 into this function, you're going to get 80 out the other side. So 1.2 goes in and 80 comes out. So to find the value of K, which tells us the shape of this graph, we just need to replace this little t for this 1.2. Now at this point, we have a single equation and K is the only unknown. So we can go ahead and solve for K. I'm going to begin by actually subtracting 25 from both sides. And now I need to remember that 80 minus 25 is just 55. Then we can go ahead and divide both sides by 75. Now to solve for this term in the power, we just need to remember to take the log base e of both sides. So that's just kind of like taking this e and then dropping it below this and then writing log on the right hand side. And then to finish this off, we just divide both sides by minus 1.2, leaving us with K. So our value of K is just given by negative 1 on 1.2 times the log base e of 55 on 75. Now this is something we can type directly into a calculator, so let's do that. So the calculator just tells us that the answer is 0.2584, but it's approximately 0.26. So at this stage, we want to do part B, which asks us how quickly the temperature is dropping at that time. In other words, we want to see how quickly the temperature is falling at that exact moment. So in order to find out how quickly the temperature is dropping at that time, we actually need to find the derivative of this function, because that's going to give us the rate at which the temperature is changing with respect to time. Just in case this confuses you at all, remember that derivatives find slopes of tangents, and the slope of the tangent gives you the change in temperature divided by the change in time. It's the rise divided by the run. So this time, we just want to differentiate the original function, and that's going to be capital T dash of little t. Now I've just moved the function below while we differentiate it, and then I'll move it back up when we're done. But we know that if we differentiate constants, they just go away. So let's get rid of the constant and this plus. So now we just need to differentiate this term over here. Now as we know, we can ignore constants that are in front of functions, so let's just move the 75 back. So now we're just left with the derivative of e to the power of negative kt. Well, you can imagine that you have this function on the outside and this function on the inside. If you differentiate the outer function, you're just going to keep e to the power of negative kt. But once you've differentiated the outside, you then have to make your way to the inside, ignoring the outside. So if we wanted to differentiate negative k times t, well, since k is a constant, this is just going to differentiate to negative k. Now that means that the derivative of capital T of t is just equal to negative 75 k times e to the power of negative kt. But we were asking how quickly the temperature is dropping at t equals 1.2. If we want to find this, we have to replace all the little t's for 1.2, and we might as well replace k for this approximation we found in the previous step. And now we once more have something we can type directly into our calculator. So let's do that and figure out how quickly our T is cooling down. So according to our calculator, our T is cooling down at negative 14.3 degrees Celsius per minute at this particular time. Now, one of the cool things about a model like this is it doesn't only apply to something like cooling tea. It also applies to heating things and cooling a whole bunch of other stuff, rather than just something simple like a cup of tea. In fact, different engineers like chemical engineers will use an equation very similar to this one over here to figure out how quickly they're cooling down particular chemicals. If they cool some chemicals down too quickly, you might end up with something totally different than what you intend. So being able to control this value of K here is actually quite important to many engineers. If, for example, you were to put this cup of tea near an air conditioner, the value of K over here would surely go up quite a bit, and you'd end up with the tea cooling down much more quickly. Similarly, if you put the tea in a thermos and actually covered it up, then K goes down and the tea stays warm for a much longer time. So figuring out how quickly a material is cooling down as a function of time is going to be the first step to figuring out how to actually keep it warm for longer. But that just about completes this example, so let's go ahead and summarize the lesson. This lesson was mostly a practical lesson, where we continued differentiating various exponentials. I reminded you that the derivative of e to the power of x was itself, and the derivative of a to the power of x was the log of a times a to the power of x. We tried two theoretical problems that involved using the chain rule and the product rule, and then we looked at a practical problem which involved cooling down a cup of tea. Now, I've only really scratched the surface of different applications of exponential functions. Aside from modeling things like cooling down or heating up things, they also model things like skydiving. You can figure out how fast a skydiver is falling as a function of time. They even model things like chemical reactions, and a whole bunch of other stuff. But instead of actually spoiling all of the useful applications for you right now, I think it's better that you keep studying them, and you'll see all the applications as you continue studying mathematics. Now, once you're comfortable differentiating exponential functions, the next step is to differentiate logarithmic functions, because after all, logarithms are the inverse functions of exponentials. So that's something we're going to continue to do in a future lesson. But that just about completes everything I wanted to say about exponential derivatives. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.